Now, we've seen how a wire that runs through a magnetic field and carries current will feel a force from that magnetic field. But I want to remind you that the only reason we used a wire with current going through it is that it was an easy way to get electric charge moving. Right? Electric circuits are a very convenient, easy way to get electric charges moving. But that behavior we saw, where there was a force on the wire, that doesn't require a wire. All we need is any electric charge moving through any magnetic field, and we'll see that same force that was dictated by the second right-hand rule. So before we start applying that second right-hand rule to situations where charges are freely moving, by freely moving I mean they're not constrained to move through a wire, I want to remind you of two things. Because direction is going to become a little more important here and a little more subtle than it was when we were looking at wires. So conventional current, when we're talking about electric circuits, is the direction that a positive charge moves. When we talk about current in electric circuits, we're sort of pretending there are positive charges and they're going that direction. Conventional current is against the direction that a negative charge moves. So if I had a positive charge moving to the right side of the screen right now, I would say current is to the right. But if I had a negative charge moving to the right side of the screen right now, I would say the current is to the left. So keep that in the back of your mind while we're going through this lesson. And the next thing I want to give you is the formula that tells us the force on a freely moving charge in a magnetic field. We have a formula for the force on a wire, but it's a little bit of a different scenario when that charge is not moving through a wire, but it's just sort of moving on its own. So F equals Q V B. Again, B is my pre-existing magnetic field. It's the first thing that I need. It's in Teslas. Then I'm going to have a charge that moves through that magnetic field. Now, when a charge moves, it creates a magnetic field, but that's not what this magnetic field is. This magnetic field is not the field created by this charge when it moves. That magnetic field was there first. And the charge is going to be measured in coulombs. V here is the speed of the charge. And that's going to be in meters per second. And so when I have a magnetic field, and in it I place a charge, and then that charge gets given a certain speed, the charge will feel a force. So F is the force exerted on the charge by the field. That'll be in newtons. Now, applying this formula isn't too bad. It's very similar to applying the formula from the previous lesson. I actually don't feel the need to do an example with it. But I do want to look at a couple of interesting scenarios that this formula or this force enables. So let's look at these now. Let's say we take an electron and it's sitting in a magnetic field. This is the magnetic field that's drawn below. So all these X's in the page, they represent magnetic field lines. They're going into the page. And let's say I take an electron and I place it there in the magnetic field. So at this point, there is no force on that electron. Electric charges don't feel magnetic forces unless they're moving. So let's say then I suddenly give this guy a bit of a nudge, a bit of a flick, and I give it a kick so it's heading towards the right side of the page. It has some velocity in that direction. Well, it'll start to move that direction. But as soon as it does, it's going to now feel a force. That force will be dictated by the second right-hand rule. So if you take your pointer finger of your right hand and you point it into the screen, into the page, the direction of the magnetic field. And then we say, well, hold on, I have a negative charge here moving to the right. So that means current is actually to the left. So your thumb is going to point to the left side of your screen. And then your middle finger will now be pointing down towards the bottom of the page. So this electron, as soon as it starts to move to the right, that means current will be to the left, and it's going to feel a force down like that towards the bottom of the page. So my electron, which wanted to just kind of head off to the right in this direction, is now going to feel a force downwards, and that's going to deflect it. So it's going to travel along a path that maybe looks different than what we originally expected. And a little while later, it'll be, say, over here now, traveling in this direction. So now we should do the right-hand rule again. Finger into page. Electron is a negative charge. It's moving down, so my thumb goes in the direction of current, which will be up. Current is opposite the direction negative charge is moving. Then I see my fingers now pointing to the left side of the page. So it's going to cause this electron to kind of keep turning. Now let's draw this again. Now my electron is going to the left side of the page. So, finger into page. Electron's going left, so that means current is to the right. And I see here my middle finger is now pointing up. And I think you maybe are starting to see what might be happening here. Notice that every time I draw the force on the electron, it's going towards the center of what's starting to look like it's going to be a circle. And you can double check with your right hand to make sure this last one's true, but you should have the force going again towards the center of this circle. So this is really interesting behavior. If I have an electron, I place it in a magnetic field. It feels no force at all. But as soon as I flick it and give it some speed, it starts to feel a force. And that force will cause it to change its direction. But since the direction of the force is dependent on the direction it's moving, the force will change its direction, and then the direction will change the force, and then the force changes the direction, and the direction changes the force, and both of them keep changing, such that it goes in a circle. And we have this, the force is always towards the center of that circle. So note that the magnetic force on the charge, in this case, provides a centripetal force. Okay. Now, let's just do this one more time, but instead of for an electron, let's do it for a proton. It's going to give us fairly similar results, but there's one shift, and that's that we're doing for a positive charge instead of a negative charge. So we'll take our proton, put it up here. Proton, positive charge. And we'll keep everything the same. We'll give it a flick to the right. So it's got some initial velocity in that direction. Actually, scratch that. I can see that I'm going to run out of page here. So let me rewind and start again. Yeah, let's put our proton down here. And I'm doing this because I can sort of foresee what's going to happen, and I want to make sure I don't run out of paper. So there's my proton. I'm going to give it a flick so it has some initial speed to the right. And then take out your right hand. Put your finger in the direction of the magnetic field, the pre-existing magnetic field, so into the page. Put your thumb in the direction of the current. Well, current is the direction a positive charge moves. This proton is a positive charge, so we just put our thumb in the direction the proton is moving, to the right. And then when we bust out our third finger, our middle finger, we see it's pointing up towards the top of the page. So it's going to take my proton and it's going to alter its path. So it goes something like that by applying a force upwards. And then over here, my proton is now going in this direction. But if we apply the right-hand rule again, pointer finger into page, thumb going towards the top of the page, we see my middle finger is now going to the left. So there's that centripetal force popping up again. The proton continues its path, but it's deflected by this force, and we already know it's going to go in a circle, so we can just kind of finish it up now. When the proton's at the top here, it's going to be moving to the left, and it'll feel a force that is downwards towards the bottom of the page, and when the proton is at the left side of the circle, it'll be moving down, and it'll feel a force that's to the right, again, towards the center of the circle. So this is kind of an interesting concept here. Again, you can have a charge sitting in a magnetic field. It'll feel nothing. Charges are not affected by magnetic fields unless they're moving. So if we give it a kick and start it to move, it suddenly feels a force. And that force sends it into an interesting trajectory where it basically is kind of stuck going in a circle. And this is actually one of the uses for magnetic fields, is they can be used to sort of trap charged particles that are moving really quickly. You can use a magnetic field like this to create an electron trap. If you have electrons that are moving really quickly and you want to kind of grab them and keep them in one place, you can just sort of beam on a magnetic field and they're just stuck going in a circle forever. All right, so like I said, we've got this new formula here. I feel like we don't need to do an example with it. I think you guys will be capable of doing that. But the quick recap I want to give you is when charge moves, it creates a magnetic field according to the first right-hand rule. And when charge that's already in a magnetic field moves, it's affected by that field in accordance with the second right-hand rule. One way that charge can move is if it's current in a wire. Another way is if it's just a charged particle heading off in some direction on its own. Freely moving, we call it. And that's what we looked at in today's lesson.